Alright, well, welcome to this introductory video on topology. And in this video I just want to give you an intuitive understanding of what topology is, and hopefully that will whet your appetite for the subject material. So let's get started. So this guy over here, you may know, his name is Leonard Euler, and he was one of the most famous, if not the most famous, mathematician ever to live. And one of the things he was interested in, among literally thousands of others, was he was wondering if there was some relationship between the number of vertices, edges, and faces of a polyhedron. So the vertices are the corners, the edges are the lines that connect the corners, and the faces are the shapes that are enclosed by the edges, so something like that. Okay, so let's do a little investigating. Let's take a look at the number of vertices, edges, and faces for these three polyhedra that I've drawn here. So let's start with the cube. How many vertices does the cube have? Well, it has 4 on the bottom. Sorry, the lines have kind of obscured it, but there's 4 on the bottom and there's 4 on the top, so 4 and 4 is 8. For edges, I have 4 on the bottom, 4 around the middle, and then 4 on the top, and that will give me 12. And for faces, I got 1, 2, 3, 4, 5, 6 faces. Okay. So, nothing yet, but let's keep going. Let's do this tetrahedron. So the vertices tetrahedron, I have 1, 2, 3, 4 vertices. How many edges? I have 1, 2, 3, 4, 5, 6 edges. And then for faces, I have 1, 2, 3, 4 faces. Okay, and the last one is this rather crudely drawn pentagonal prism, but let's see if we can plow through it. For vertices, let's see, there's 5 on this pentagon and there's 5 on that pentagon, so that gives me 10. For edges, there's 5 edges on this pentagon, 5 edges on that pentagon, and then 5 edges that connect them, so that's 15. For faces, there are 1 face here, another face there, and then 5 faces that connect, so that's 7. Okay. And so what Euler noticed is that if you took the number of vertices minus the number of edges plus the number of faces, you get 2 for all of these. In fact, it gets better than that. If you had a sphere, and you were to draw vertices on the sphere and connect them with edges, something like that, excuse me, and you were to do the same thing, vertices minus edges plus faces, and if you count the outside as a face, no matter how you draw this, you get 2. And let's just check that right now. How many vertices do I have? Well, I have 1, 2, 3, 4, 5 vertices. I have 1, 2, 3, 4, 5, 6 edges. And then I have 1, 2, and then the outside is a face, 3 faces. 5 plus 3 is 8, minus 6 is 2. So it's amazing that no matter how you draw this map, you always get 2 for this number. And in fact, even if you have something that's not a sphere, but something kind of blobular, but still sphere-like, in the sense that if I stretch the sphere in some way, I can get this shape. And you do the same idea of drawing vertices and edges. You can do this vertices minus edges plus faces, and you still get 2, no matter how you draw it. And you might start to think, well, maybe that's just how it always is. Maybe no matter what shape you have, you do vertices minus edges plus faces, you get 2. But there is a shape that I can think of, and there are many others, where this is not the case. The donut. If you were to do this with the donut, you don't get 2, you get 0, up to some certain restrictions. But the point is that this thing, this vertices minus edges plus faces, which is called the Euler characteristic of a surface, is different for these guys than it is for the torus, the donut. So what's the difference? What's the difference between the blob, the sphere, the pentagonal prism, the tetrahedron, and the cube? What do they not have that the torus does? Well, it's staring you right in the face, isn't it? The hole. This has a hole and these don't. And moreover, I can take any of these shapes, and if I stretch them or bend them, I can get something that's a sphere. I can continuously deform these shapes and get a sphere. But no matter how hard I try, no matter how much I bend and stretch and shrink the torus, the donut, I cannot get a sphere. This vertices minus edges plus faces, the Euler characteristic, is what's called a topological invariant. Might as well write that down. A topological invariant. What is a topological invariant? A topological invariant is something that's a property of a shape that doesn't change no matter how much you continuously deform it. If you stretch or you bend it, as long as you don't tear it or glue it, but if that is something that always stays the same under those kind of continuous deformations, it's a topological invariant. And the Euler characteristic, the vertices minus edges plus faces, is an example of that. So topology, in a word, is interested in the properties of shapes that are invariant under continuous deformation. We're interested in properties of shapes that don't change when you stretch and bend it. And topology is of prime interest in mathematics today, both for its use as machinery, it's very powerful in analysis, but also is intrinsically interesting. And I hope this has given you some idea of what topology is all about. In fact, for something that you might find interesting is that if you take this donut and you use this idea of continuous deformation, you can actually get a coffee cup. And so there's an old joke about topologists take really long coffee breaks because they can't figure out whether to dip their coffee into their donut or their donut into their coffee cup. So I hope that's whet your appetite a little bit for the subject material, and we will hammer out all the details in the videos to come. So I'll see you then.